This is 3.4.2, controlling nuclear reactions. So the first question asks you to fill it in a table, looking at the different types of radiations. You've got alpha, beta, gamma, give the symbols. What are they made of? So helium nucleus. You could have written two protons and 2 neutrons if you wanted to. Then we've got fast moving electron, EM wave. Looking at the charges then, +2, -1, 0, speed, slow, medium, fast, and then stopped by paper, aluminium, lead. Radioactive decay is a random process in which nucleuses lose neutrons by emitting radiation. This is usually a form of alpha particles, beta particles, or gamma rays. Nucleus's energy increases, making it more reactive. Okay. Term ionizing, the charge changes to a particle's charge. Next question then asks you to fill in sentences using the keywords just to get your understanding of radioactive decay up. So when a parent nucleus gives out an alpha or beta particle, the nucleus turns into a nucleus of a new element. This process is called radioactive decay. Although radioactive decay is a random process, statistically over time, is the half-life. Half of the unstable nucleus will be decayed. Working out the half-life allows us to calculate when radioactive element will become stable. Okay. Then I filled out the table. So this is a half-life of 20 days. A half-life of 20 days. So the first thing you want to do when you've got one of these tables is fill in the number of half-lives starting at 0. So 0, 1, 2, 3, 4, 5, 1 all the way. Didn't actually need 5 and 6. Time always starts at 0 then, and then activity mass or percentage starts at whatever the percentage or mass they say to start with. Each half-life's 20. Remember, you are adding 20 each time. You're not doubling. You're adding 20 each time. Okay, you're halving this each time. Okay, so the answer would have been 325. Same kind of situation then for this one. Asking how long it takes to get from 8 to 0.125. Remember, you're halving it each time. These both start at 0. This is an easy column to fill out because you're just going up to, you could have gone to 6 if you wanted to. And then 45 seconds, you're adding 45 seconds each time. So you're saying that it'll take 225 for it to decay to that. Next question then is more of a past paper question asking you to fill out what alpha, beta and gamma look like. Okay, so fast moving electron, helium nucleus, electromagnetic wave. Okay, then it says using the graph to find the count rate after 40. So go up from 40 and across to be 80. State the value of the half-life. So it starts at 160. So it takes 40 hours to decrease every time. That just so happens it's a coincidence that they're the same. Okay, that's to kind of trick you by there. Okay, and then it says calculate the time it would take for the count rate to fall from 3,000 to 800. Okay, so did the table, number of half-lives, started at 0, the mass was that to start with, halved it, added 40 each time. Okay, so it would have taken 80 hours to get to that point. A substance has a longer half-life, so it takes longer to decay. So I just looked at this one, 40, 80 would have taken then 60, so it would have had a longer half-life. Click the 3 that are correct, so shows an uncontrolled chain reaction. Fusion means 2 particles joining together. Each stage the number of neutrons doubles. Okay, complete the nuclear decay equation for the fission reaction shown in the diagram, so just making sure that it all adds up to what you got. 136 on this side, so you want to make sure it all adds up. That's a beta neutron. Okay, same kind of thing going on here. You want to make sure that it all adds up to 136. So you need another element that adds up to that and another element that adds up to 92 plus the neutron. Then it looks at the nuclear fusion and nuclear fission and the nuclear waste reactor. Describe the role of the control rods. They lower or rise, stop neutrons travelling into the fuel rods if you need to. State how control rods can be used to stop nuclear reactions, prevent a reactor meltdown. Change the speed of the chain reaction, stop it from getting out of hand. Final question then looked at a nuclear power plant accident, and it looked at a type of cesium that was released. Okay, and it gave you all this information about what the levels were like in the sea in 2016, 5 years after the reaction, what they were like before it happened, and then talking about what the levels need to be at for it to be safe to eat. okay? John claims the fish will be safe to eat in 2080. Use the information to determine whether John is correct, okay? So I did like a half-life thing, okay? So it started at 120, so I started that as my mass. So I could have gone along and just halved it, okay? We are looking to get to 15, which is here, okay? I carried on, but you'll need to get to 15. Then number of half-lives is nice and easy, okay? And then it said that it takes 28 years. It's half-life of 28. So 28, 56, 84. So he's saying by 2080, it takes 84 years. We're already in 2016, so it wouldn't be safe until about 2110, okay? Use the information to do a nuclear reactor. Okay, so just put all the information in. So start with that, absorbs a neutron to produce one neutron, and this is just basically putting it all in a line. Okay, describe how fission reactions could lead to uncontrolled chain reactions, explosions, reactor could melt.